Okay, so previously we did the confidence interval for a single sample, okay, for its mean, but now we will do the confidence interval of the difference of two means, mu1 and mu2. So we will find the confidence interval for the difference of two means, mu1 and mu2, while mu1 is the mean of sample 1 and mu2 is the mean of sample 2. Okay, so both samples actually are large, which means that n1 and I is greater than or equal to 30 for I is equal to 1 and 2. It means that sample 1 and 2 both are greater than 30, both are large samples. Okay, and these samples are independent of each other and taken from independent populations. Okay, so there are actually two cases over here. The case 1 is that when the sigma 1 square and sigma 2 square, it means that the standard deviation for sample 1, for population 1 and standard deviation for population 2 both are known. It means that we have the distinct values of sigma 1 square and sigma 2 square, or we have the values of standard deviation 1 and standard deviation 2. Okay, then in this case the confidence interval, it will be equal to x1 bar minus x2 bar plus minus z of alpha by 2 into square root of sigma 1 square divided by n1 plus sigma 2 square divided by n2. Okay, so this is the first case. Okay, when we have the standard deviation for both the samples. Okay, and here is the case 2. In case 2 states that when the standard deviation for the first sample and standard deviation for the second sample is unknown. Okay, so when this case happens, then the difference of the means, confidence for interval for the difference of mean is equal to x1 bar minus x2 bar, okay, plus minus z alpha by 2 into, now we don't have the standard deviations, okay, but we will have the sample standard deviations, which are s1 square and s2 square. Okay, so these two are the cases. We will try to solve a problem or two on both these two cases. let's solve an example and see which case it follows and find the solution for it. Okay, so the example over here that we will study is, it says that construct a 90% or 98% confidence interval for the difference between the mean lifetimes of two kinds of light bulbs. Okay, there are two kinds of light bulbs. Okay, and we want to know the confidence interval for the mean difference between their mean lives. Okay, and given that a random sample of 40 light bulbs for the first kind, so n1 is equal to 40 bulbs, and the average x1 bar, the average life of the first kind of bulb, is equal to 418 hours. Okay, now the second sample is of, it says that those were of 50 bulbs, and the mean life of the second kind of bulb are 402 hours. Okay, so now we have the sample sizes for the two samples and the means of the two samples. Okay, now the population standard deviations are known to be, now the population standard deviation, okay, the first population from which the light bulb one sample is taken, it has a population standard deviation of 26 days 26 hours, and the standard deviation for the light bulb 2 is equal to 22 hours. Okay, now this falls under the category of case 1, where the standard deviation of the first and the second one are known. Okay, variances of population 1 and 2 both are known, so we can actually convert these variances into the standard deviations by just taking the square root. Okay, so for this alpha, okay, now yet the confidence interval is for 90% confidence. It means that alpha is equal to 1 minus 0.9 is equal to 0.1 is equal to 1 minus alpha is equal to 90%. So alpha is equal to 1 minus 0.9, which gives us a value of 0.1. Okay, now z of alpha by 2 will give us z of 0.1 divided by 2, z of 0.05, and from the z table, okay, it gives us a value of 1.645. Putting this value into the equation and making the equation, we get x1 bar minus x2 bar. It will give us 418 minus 402 plus minus z of alpha by 2. It gives us 1.645 multiplied by square root of sigma 1 square divided by n1 plus sigma 2 square divided by n2. So sigma 1 square is 26 whole square. Okay, sigma 1 square is equal to 26 whole square, and sigma 2 square is equal to 22 square. Okay, so 26 square divided by n1 is 40, so plus 22 whole square divided by 50. Okay, now simplifying this part of the problem, we have 418 minus 402, it will give us 16 value, plus minus 1.645 multiplied by, now let's simplify it. We get, let's calculate it. 26 square will get us a value of 676 divided by 40, plus 22 square will get us a value of 22 multiplied by 22 is equal to 484. 484 divided by 50 whole under the root. Okay, now 484 divided by 50 will get us 9.68. So this reduced to 9.68 plus, and 676 by 40, 676 divided by 40 get us a value of 16.9. So 16.9, let's add it to the 9.68 that we previously found. We get a total of 26.58. Okay, and this is multiplied by 1.645 plus minus 16. Okay, so these two, adding these two, it gets us a value of 26.58. So 90% confidence interval is equal to 16 plus minus 1.645 multiplied by under the root 26.58. It is equal to 16 plus minus 1.645 multiplied by, let's find under root for this value, and it will give us 5.155. okay, now it is equal to 16 plus minus, let's multiply it with 1.645. okay, this is, yes, this is 1.645. multiply it with 1.645, it gets us a total value of 8.48. So 16 plus minus 8.48, this is the CI range. The CI is equal to 16 minus 8.48 and 16 plus 8.48. So let's add it to 16. It gets us the higher value, the higher limit is 24.48 and the lower is 7.523. So these are the two limits, or the two range values for the 90% confidence interval. So now we are 90% sure, or we are sure that at 90% of the time the mean value will fall in this range. Okay, we will also do another example for the sample means, where the population standard deviations are unknown and only the sample standard deviations are known. For the second type, like case 2, I will have an example like a psychologist is interested in the effect of no sleep that has on an individual abilities to perform the motor task like physical abilities. So she selects two groups. The first group is of 25 students, so N1 is equal to 25 students, okay, and she make them stay up all the night, and then select another group of 27 students, so N2 is equal to 27 students, and she asked them to sleep the whole night, and then these students are made to attempt 20 free throws at the basketball court. So group 1 makes an average of 8 shots with standard deviation of 2.3. Okay, so x1 bar is equal to 8 shots. Okay, and the standard deviation of the sample, this is the sample standard deviation, okay, not the population one, equal to 2.3 shots. Okay, and for the second group which slept at night, they made the average of 12 shots, okay, with a standard deviation of 3.4 shots. Okay, so it says that find the 95% confidence interval for this scenario. So we know that this scenario falls into the second case because we have the sample standard deviation over here and not the population standard deviation. So it means that the population standard deviations are sigma 1 and sigma 2 are unknown. So when they are unknown, then we find the confidence interval using the formula x1 bar minus x2 bar plus minus z alpha by 2 multiplied by under the root of s1 square divided by n1 plus s2 square divided by n2. So using this formula, actually we will try to find the confidence interval, 95% confidence interval. Okay, so putting the values that we have x1 is equal to 8 and x2 is equal to 12. So 8 minus 12 plus minus z, this is 95%, so it is 0.05 divided by 2 multiplied by square root of s1 square. S1 is 2.3, so 2.3 square divided by n1 is 25 plus s2 is 3.4, taking square of it and divided by 27, which is the sample size. Okay, so it gives us minus 4 plus minus z of 0.025. okay, multiply by, let's make this factor simplified. So taking the square of 2.3 and divided by 25, and then square root square of 3.4 and divided by 27. Let's calculate this. 2.3 square actually gave us a value of 5.29, okay, plus 3.4 gives us a value of 11.56 divided by 27. Okay, so let's divide it by 27. we get a value of 0.42. Let's divide 5.29 by 25. We get a value of 0.2116. 0.2116. So adding both these values, we get 0.6316, and taking the square root, we get a value of 0.79. Okay, now z of 0.025, it gives us a value of 1.96. Okay, so now multiplying both these, we get 1.55. So minus 4 plus minus 1.55. So the confidence interval is equal to minus 4 minus 1.55 comma minus 4 plus 1.55. So we get a value of 2.44. Okay, on this side we get minus 2.44, and on the other side, let's calculate minus 4 minus 1, so it will give minus 5.155. Okay, so we see that both these values are negative. Okay, if this were negative and this side were positive, it means that 0 would be in the middle of this range, and if that happened, it means that there were no significant difference between their means. But as we have negative value over here and also negative value over here, it means that there is a lot of difference between their means, and the sleep actually affects the performance, the motor performance of the students. Okay, so in the first 4 sessions, actually what we did was we found the confidence interval for a single population parameter. Mainly we discussed the mean of the population, the mean of the sample. Okay, and also we took this sample from only one population. Also there was only one sample. So we can write it in short as one sample and one parameter. Okay, now we will move forward towards two samples comparison. Okay, and we will have a single parameter, but we will have single parameter, but for both samples, and we will compare both samples for that parameter, that whether both the samples are significantly different or they are not significantly different and they are actually same. For example, there are two means. Okay, so we can say that the means for two samples are either significantly different or significantly same. So what we do is we find the confidence interval for mu1 minus mu2. Okay, so mu1 is the mean for first population and mu2 is the mean for second population. Okay, so we compare both these means and find the difference of it. Okay, if the confidence intervals, okay, it is between a negative and a positive value. If the left hand side is negative and the second right hand side is this one value is positive, it means that they are not significantly different from each other. Implies that x1 minus x2 bar, it will be equivalent to about 0. It means there is no difference. But if the confidence interval yields a negative value over here and also a negative value over here, then they are significantly different from each other. Okay, in this one, in the minus and plus, 0 lies in this range. So when 0 lies in this range, it means that the difference is 0, because the confidence interval is for x1 bar minus x2 bar, right? Okay, here are also large samples and small samples. So the first case is for large samples, implies that n1 is greater than or equal to 30 and n2 is also greater than or equal to 30. So these samples are large, and in the first one, the populations are independent. Okay, in this we have the first case is like a case is that the variances of populations, actually not the samples but the populations, are known. Implies that sigma 1 square and sigma 2 square, this is the variance of population 1 and this is the variance for population 2. Okay, these are the populations from which the samples are taken. When the variations are known, then the confidence interval, actually it can be found by x1 bar minus x2 bar. These are the means of the sample plus minus z alpha by 2. We will use z value if the large samples are large, okay, and they follow the normal distribution. Multiply by sigma 1 square divided by n1 plus sigma 2 square divided by n2, where n1 is the sample size for the first sample and n2 is the sample size for the second sample. Okay, so this is the formula for confidence interval when there are two samples and two means, population means. Okay, now we have another case, okay, case B, and in this case we have when the variances of both the population are unknown. Okay, but the sample variances, sample 1 and sample 2 variances are known, then the formula that will be used for the confidence interval, it will be equal to x1 bar minus x2 bar plus minus z alpha by 2, okay, into s1 square divided by n1 plus s2 square divided by n2. So it is almost same, only difference is that we have the sample variances over here. If sample standard deviation is given, just square it and you will find the variance of it. Okay, we already did the questions on both of these cases in the previous video. Here is the third case for which we will explore today. Okay, and the third case is, or we can say that the second scenario is that when the populations are independent and normal populations. Okay, independent normal populations. Okay, so if it is case A and the variances for both the populations are known, then it will use the same formula as we used before, which is equal to x1 bar minus x2 bar, which are the means for sample 1 and sample 2 respectively, plus minus z alpha by 2 multiplied by under the root sigma 1 square divided by n1 plus sigma 2 square divided by n2. Okay, and the second case is that when the population variances are equal. Okay, the population variances are equal. It means that the sigma 1 square is equal to sigma 2 square. Okay, so when the population variances are equal but unknown, we know that the population variances are equal but it is still unknown, then we use the following formula. Ci is equal to x1 bar minus x2 bar. Okay, and we will use t alpha by 2 and 1 plus n2 minus 2 multiply by sp into 1 divided by n1 plus 1 divided by n2. Okay, now we will use the t distribution over here. When we know that the population variances are both equal for first population and for second population, the variances are equal but we don't know about the exact value of it, then we will use this formula. Okay, so this is the significance level, alpha by 2 significance level, and this is the degree of freedom for samples. So we have two samples, so n1 plus n2, it will give you the total number of samples, and minus 2 will give you the degree of freedom. Okay, now sp is the pooled sample variance. Okay, is equal to pooled sample variance. I will also define this thing, and the formula for pooled sample variance is equal to n1 minus 1 into s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. Okay, and sp is equal to under the root n1 minus 1 into s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. Okay, so this is the formula. Now we will define the pooled sample variance, and how it is used. The pooled sample variance by definition is a weighted average of variances of multiple groups. And it assumes that, assuming equal population variances. And why it is used? It is used to estimate the variance of two or more groups simultaneously. Okay, so it is the weighted average of the variances, of multiple groups. Okay, so this is the weight that is associated to it, and 1 minus 1, which is the degree of freedom, and S1 square is the variance of that sample. Okay, similarly, and 2 minus 1 gives us the degree of freedom for sample 2, and S2 square is the sample variance of sample 2. Okay, so it is the weighted variances of both these groups, group 1 and group 2. Okay, and we average it by dividing it by the total number of degree of freedom, which is n1 plus n2 minus 2. Okay, and why it is used? It is used to estimate the variance of two or more than two groups simultaneously. Okay, because we find the standard error from the variances. Okay, so calculating the variances of these samples is very crucial. So that is why we use the pooled samples. I will now do a question on it and I will explain. Okay, it is an example question, and it says that a study has been made to compare the nicotine content of two brands of cigarettes. Okay, we have two brands, okay, S1 and S2. So we get two samples of the two brands respectively. Okay, this is brand A and this is for the brand B. Sample 1 is from the brand A and sample 2 from the brand B. Okay, so the average nicotine for the brand 1, sorry, it is x1 bar and it is equal to 3.1 milligrams. Okay, for x2 bar, the nicotine content for the sample 2 second brand is equal to 2.7 milligrams. Okay, and for this brand, the standard deviation for the sample S1 is equal to 0.5 mg, and for this the standard deviation for the second sample is equal to 0.7 milligrams. Okay, now we don't have the population variances for both these populations from which these two samples are taken. Okay, because we know that the populations are independent and these samples are independently taken from both these populations respectively. But we know that the standard deviation for these samples are given, these are calculated. Okay, and it says that assume that the random samples, sample 1 and sample 2, are taken from populations with equal variances. Okay, we only know that the population variances, okay, sigma 1 square is equal to sigma 2 square. Okay, but they are unknown. So this condition actually it satisfies for the use of the special case, which is the pooled variance. Okay, now the confidence interval can be found using multiply by the SP into, okay, so this is the relative formula to find the confidence interval in such case. Okay, now putting the values with which we have already, so we have x1 and x2, we have n1 and 2, we need to find SP, we have n1 over here and n2 also over here. So first of all, we calculate SP because it is not available to us. So we know that the pooled variance is equal to under the root n1 minus 1 into s1 square divided by plus n1 plus n2 minus 2 and n2 minus 1 into s2 square. Now we have n1 over here, s1 is also given to us, n2 is also given to us, s2 is also given to us, and the denominator is also given. So we put the values over here. Now putting the values over here, we find that n1 is equal to 10. These 10 cigarettes are taken to calculate the this mean. Okay, and the other one has like 8 cigarettes are taken of type B, and the averages and standard deviations are calculated. So n1 is equal to 10 and n2 is equal to 8. Okay, s1 is equal to 0.5 and s2 is equal to 0.7 milligram. Okay, now n1 minus 1, it will give us, let's put the values for your understanding so that you do not get confused. n1 is equal to 10 minus 1 into s1 square is 0.5 square. Okay, plus n2 minus 1, so 8 minus 1 into 0.7 square divided by 10 plus 8 minus 2. Okay, so we get SP is equal to square root of, this is 9 into 0.5 square plus 7 into 0.7 square, and we get 18 minus 2 is equal to 16. Okay, 16 can be written as 4 square. Okay, so this will give us a value of, let's calculate it, 0.5 square will get us a value of 0.25. So 9 into 0.25 plus 7 into 0.7 square, it will give us 0.49. So 7 into 0.49 divided by 16. Okay, now let's calculate this and take the values. 9 into 0.25, it will get us a value of 2.25 plus 7 into 0.49 is equal to 7 into 0.49 is equal to 3.43. So 3.43 divided by 16, so it will get us a value of 5.68 divided by 16. Okay, so under the root 5.68 divided by 16, it will give us under the root 0.355. So taking the square root of it, it will get us a value of 0.5958. Okay, so SP is equal to 0.5958. 0.5958. So we can round it off to 0.6 actually. Okay, now we have also SP over here. The only thing that is left is the T value. Okay, we can get it from the T table, but let's first simplify these terms. Okay, so T alpha over here, because we want to find the 95% confidence interval, so alpha is equal to 1 minus P. Okay, so P over here is 95%, which is 0.95. When converted into decimal, it will get us 0.05. Okay, so alpha is 0.05. So T of 0.05 divided by 2, comma, and 1 is equal to 10 and 2 is equal to 8 minus 2. So we already have found it, which gives us 16 value. So let's from T table, let's find the value. Okay, and why we use the T actually, because the samples over here are 10 and 8 respectively, so these are very small samples. So when we have small samples, that is less than 30, then we use the T table. Okay, 0.05 divided by 2, it will give us T of 0.025 and 16, and it will give us a value of, let's see it in the, so we have the degree of freedom equal to 16. Okay, and the probability, upper tail probability, degree of freedom, significance is 0.025. So 0.025 is this, and from 16 and 0.025 it gives a value of 2.120. This is the value. Okay, 0.025, bring it down, and in front of 16 degree of freedom, so it is 2.120. So let's put it over here, 2.120. Okay, now we have this value also. So we have x1, x2, this T value, the pooled variance. We only need to know about this term. Now under the root 1 by n1 plus 1 by n2 is equal to under the root 1 by 10 plus 1 by 8. So it will get us a value of, it will give you 1 over 10 is equal to 0.1. So 0.1 plus 1 over 8 is actually equal to, let's calculate it, 0.125. So it will collectively get us 0.225. So when taken square root of it, it gives a value of 0.47. So we also have now the value for this term. So putting the value of all the terms over here, the confidence interval is equal to x1 bar is equal to 3.1 minus x2 bar is 2.7 plus minus. Okay, now we have the T term over here. The T term have value of 2.120 into the SP, which is pooled variance of 0.6, and into this term, which is 0.47. So it will give us a value of 3.1 minus 2.7. It will give a value of 0.4 plus minus, and let's calculate this value. It will give us a value of 0.5936. Okay, so 0.4 minus 0.5936 minus 0.197. So it can be kind of 0.2 up to 0.9. Okay, now 0 is, this is transition from negative to positive. Okay, this is positive value, this is negative value. It means that 0 is coming somewhere in between over here. So the samples are not significantly different from each other. Okay, this is the inferences actually. Yeah, so both the samples are not significant difference, or you can say that there is 95% chance that both the samples are kind of equal, okay, with equal means. Thank you. So this is I will go to the next step and let's see. Okay, so now we will take a case where we are given the data into the some log function or exponential functions. Okay, so if we will use the maximum likelihood estimation method, MLE. Okay, this method will be used to find the confidence interval in this case. Okay, so in the example, actually, for example, we are given that the sample size is equal to 64. So n is equal to 64, and the function that is given is f of xi and theta, where theta is the population parameter and x is the variable, and it is equal to theta into x raised to the power theta minus 1. Okay, this is the function that is given to us. Okay, and then x has a value between 0 and 1. Okay, so we can actually use the maximum likelihood estimation to find the confidence interval in this case. So we can write it as log of theta, L of theta is equal to summation of I up to n log of f of xi and theta. Okay, where I is equal to 1 up to n as we write over here. Okay, so now replacing this function with the original one, which is this one. Okay, so we can write it as L of theta. This is the background work behind the final function that we will receive. Okay, so I am just doing the background job. Okay, this is for your understanding. This is not for it may not come an exam or anything. You may end up using only the final result that we get, but it is for general understanding that whenever we get the function in some exponential form, okay, and we have a parameter theta over here, so we use log actually to declassify it, okay, and get some normal value from it. So L of theta, it will be equal to summation of I up to n log of theta x raised to power theta minus 1, and this is the x value I, and x is also between 0 and 1. This is the x range. Okay, now this can be written as n log of theta plus theta minus 1 into summation of log of xi, where I is equal to 1 up to n. Okay, now taking the differential of it with respect to theta of this function. Okay, so it will be equal to d by d theta n log of theta plus d by d theta. Okay, theta will be multiplied by this and minus 1 into this, so it will become theta log of xi minus d by d theta of log of xi. Okay, so we will get here n, this is a number, so it will come forward, and d by d theta of log of theta, we know that d by dx of log of x is equal to 1 over x. Okay, so it will become 1 over theta using this rule. Okay, and the d by d theta of theta log of x I, it will become log of xi. This theta, it will be yield a value of 1. Okay, and it will be equal to 0, so it will become n by theta plus log of xi, and I is equal to 1 up to n, and we can say that I is equal to 1 up to n. We can write the summation over here. Okay, so this is the value that we achieve over here. Okay, now put this equal to 0. Okay, so n by theta plus summation of log of xi is equal to 0, so theta bar is equal to, this will come to this. Okay, so it will become theta bar let's see, it is okay, it will as a whole come to the so it will become minus n by theta is equal to summation of log of xi. Okay, now it will come to this side and this will go to this side, so minus n divided by summation of log of xi will be equal to theta bar or theta cap. Okay, now this is the estimated value. Actually, the bar shows that it is estimated value for theta. Okay, is equal to minus n divided by summation of log of x, where I is equal to, let me write it in some clear form, summation of log of xi, I is equal to 1 up to n. Okay, so now in this question, the example that we solve, using this case. Okay, this is that n is equal to 64, the number of samples is 64, and summation of log of xi from I is equal to 1 up to n, this is equal to minus 18.674. okay, this is the value that it yielded. So this is also available, and n value is also available. Okay, now we will find the 90% confidence interval for theta. Okay, so how we will find it? We will find it exactly the same manner like we find it for the mean. Okay, now we know that the probability is 90%, so alpha is equal to 1 minus p implies that alpha is equal to 1 minus 0.9 implies that 0.10. So this is the significance level. Okay, and the confidence interval, it will be equal to the theta bar plus minus z alpha by 2 into standard error of theta bar. Okay, now this is the factor or the term that we need to investigate and find out. Okay, so ci is equal to theta bar plus minus z alpha by 2 into standard error of theta bar. Okay, so standard error of theta bar is yet to be found. Okay, so we know that theta bar is equal to minus n divided by log of xi. Okay, and n is equal to 64 samples over here, and the log of xi value that is given to us is minus 18.674. so putting the values over here, we find the theta bar value. Okay, so minus 64 divided by minus 18.674, it will give us approximately 3.43 value. Okay, now we have theta bar over here, so the standard error, it will be equal to under the root theta bar whole square divided by n. Okay, so we put the values. Theta bar whole square is equal to 3.43 whole square. Okay, so let's get the value of it. So 3.43 multiplied by 3.43 will give us the square value, and it is equal to 11.765. Okay, so this is the square value of it. Okay, so 11 point, putting value over here, divided by 64, we divide this by 64, which is the number of samples. So we get a value of square root 0.1838. Okay, so now we get the square root of the same value, and it gives us a value of 0.428. Okay, so this is the estimated standard error. Now we have the standard error over here, and we know that the confidence interval is equal to the mean value plus minus the margin of error, and margin of error actually is equal to z alpha by 2 multiplied by standard error. Okay, so now we have this value, we need to find z alpha by 2. So z alpha by 2 is equal to 0.1 divided by 2. So because this is alpha is equal to 0.1, so it will become 0.05, and z of 0.05 yields a value of 1.645. Okay, now putting this value and multiplying it with the standard error, we get the margin of error. Okay, so the ci for the theta at 90%, it is equal to theta bar plus minus, okay, margin of error is equal to z by alpha by 2 into SE, standard error, that is of theta bar. Okay, so theta bar value over here is 3.43 plus minus z alpha by 2 is equal to 1.645 and the standard error is equal to 0.428. So making these calculations, the confidence interval, the 90% confidence interval that we get for theta is 3.43 minus, let's calculate this value. Okay, so we have 0.42875 multiplied by 1.645. So this gives us a value of 0.705 and 3.43 plus 0.705. Okay, so this is the range. So 3.43 plus 43 plus 0.705 gives us the upper margin of the upper bound of 4.135 and the lower range will be equal to 2.725. So this is the 90% confidence interval for theta. Okay, so that is how we find the confidence interval when we have some exponential function, okay, or some value given in the logarithmic form, log form. Okay, now we will move forward to the next example. Now we will do an example where we are to find the confidence interval for mean of the population as well as the standard deviation of the population, okay, from the same data. Okay, so the case is to find the confidence interval for mean, mu, as well as standard deviation, sigma square, variance sigma square for the same population. Okay, so the question says that suppose we have a random sample of size 81. Okay, so n is equal to 81. Okay, and this sample is from n, mu and sigma square. It means that it is normally distributed, okay, with the mean and standard deviation. Okay, so it says the observed samples gave x bar is equal to 59.826. So this is the sample mean value, not the population but the sample mean value. Okay, and the S naught square or we can say the variance of the sample is equal to 11.738. This is the sample variance, okay, not the population but the sample variance. Okay, so we want to find the large sample. Okay, sample size is 81. Okay, so large sample, 99% confidence interval for mu is to be found. And the second thing that we need to find is the large sample, 99% confidence interval for variance. So both of them need to be found. Okay, so we start with the first one. Okay, so when we start with the first one, we know that the sample of the mean sample is equal to x bar, and it is equal to 59.826. This is the estimated population sample. Okay, the cap means that it is estimated value. Okay, and it is equal to the sample mean, because we assume that this sample mean actually represents the population mean. Okay, so that is how these are related. Okay, and then the estimated variance of the population is equal to the variance of the sample, and it is equal to 11.738. Okay, we got it equal to the population mean and population variance. So now when we got it equal to and the sample is high, it means that now we have the estimated population sample, population standard deviation. Okay, so we will use the z values over here. Okay, the z table will be used, and we know that confidence interval is equal to the estimated mean plus minus z alpha by 2 into standard error of the mean. Okay, and by standard error we mean that the population estimated variance divided by the n, which is the number of samples or sample size. Okay, so let's first calculate the standard error. So standard error, it is equal to, now the population variance, the estimated population variance is equal to 11.738. okay, this is not standard deviation but variance, because it has a square value. Okay, this is s, not square. Okay, this is not s. If it was s, we would have squared it over here, but it is not s. It is s squared or sigma squared. Okay, divided by the sample size, which is 81. So let's calculate it. We will get a value of so 11.738 divided by 81, we get under the root of 0.1449. okay, so we get the square root of the same number. It gives us a value of 0.38. so 0.3806, or we can say 0.0381 is the standard error value. Now we have the standard error value, we need to find the z alpha by 2. So alpha over here is 1 minus p, and p is 99% are 0.99. So 1 minus 0.99 is equal to 0.01. So alpha significance level is 0.01. So z alpha by 2 is equal to z of 0.01 divided by 2, and we get 0.005. Okay, and this in z table will give us a value of 2.576. okay, this is the estimated value from the z table. Okay, 2.576. now we have the z value, we have the standard error, and we also have the estimated population mean. Okay, so the confidence interval for the mean, it is equal to 59.826 plus minus 2.576 into 0.381. so calculating these, we will get so we get 59.826 minus 0.98 and 59.826 plus 0.98. so first subtracting it, we get a value of 58.84 and adding 60.80. so this is the 99% confidence interval for the population mean. Okay, so what does it say us? It tells us that the population mean lies between 58.84 and 60.80. And its chances are that it lies by 99%. There are 99% chances that the population mean lies between 58.84 and 60.80, and we know that the confidence interval width is quite low. It means that the samples have low variance. The variance is very low, and it can also mean that the sample size is quite high. Okay, that is why we have more data and the interval width is low, or we can say that small. Now we also want to find, the second part is to find the 99% confidence interval for the population variance. Okay, so we can say that the estimated population variance is equal to that of the sample population variance, and it is equal to 11.738. okay, for example, we suppose that this sample perfectly represents the population. Okay, so the general formula for confidence interval is that the estimated population mean plus minus margin of error. Okay, and this margin of error is equal to z alpha by 2 multiplied by the standard error, and standard error in terms of the variance of the population. Okay, so we will find it out. So first of all, we need to find the standard of error for the population variance. So the standard of error over here, it will be equal to, the formula for this is 2 we will take the square of the variance, multiply by 2 and divided by n and whole under the square root. So putting the value in this formula, we get 2 multiplied by the population variance is equal to 11. The estimated population variance is equal to 11.738 and squaring it and dividing it by 81. So we will get 11.738 whole square will get us a value of 137.8. So 2 multiplied by 137.8 divided by 81. So we will get the value which we multiply it by 2. So the numerator we get is equal to 275.56. Let's divide it by 81. Divide by 81, we get under the root 3.402. 3.402. And when we get the square root of it, so we get a total value of 1.844. This is the value of the standard error for the population variance. Okay, now we have the standard error. We need to find z alpha by 2. Okay, so we already have found that alpha is equal to 0.01 and alpha by 2 is equal to 0.005. So z of 0.005, it gives us a value of 2.576. Okay, so now putting the values, we have plus minus z of 0.005 multiplied by standard error. Okay, so the confidence interval 99% confidence interval is equal to 11.738 plus minus 2.576 multiplied by the standard error here is 1.844. So let's calculate this factor and then add and subtract it. Okay, so let's prepare it for the subtraction and addition. So let's find the value of this factor. Okay, so 2.576 multiplied by 1.844, we get a value of 4.75. So 99% confidence interval for the population variance, estimated population variance is equal to 6.987 and 16.488. So this is the 99% confidence interval for the estimated population variance. Okay, and it says that the population variance is most likely by 99% likely to fall between 6.987 and 16.488. Okay, so that is how we find the values for the confidence intervals using different cases and scenarios. So the next we will do will be for the difference in variances and all that. So that will be covered in the next lecture. Thank you.